Here's an integration problem using the method of cylindrical shells to find a rotational solid. It's from Rogowski's section 6.4, page 363. We're going to work on problem 11 here. So notice it says use the shell method to compute the volume obtained by rotating the region enclosed by the graphs as indicated about the y-axis. So that's going to be important, the y-axis. So what do we have on 11? We have y equals x squared plus 1 all raised to the negative 2. Y equals 2 minus x squared plus 1 to the negative 2. And the line x equals 2. So I took the liberty of writing those down ahead of time for you. And I picked these in particular because maybe you don't have a good intuition for what x squared plus 1 to the negative 2 looks like. So here's what I would recommend if you don't have a good intuition for what those look like. I'd recommend, frankly, that you make a little table. X, Y, the values, if I have no clue, the values that I usually pick are negative 2, negative 1, 0, 1, and 2. Why? Well, they're close to the origin, so I can sort of see where those points are. Okay, if I plug negative 2 in here, negative 2 squared is 4, plus 1 is 5. So I have 5 raised to the negative 2. The negative inverts it, the 2 squares it, so I have 1/25. Okay? If I plug in negative 1 squared is 1, plus 1 is 2. So I have 2 to the negative 2, that's 1/4. 0, that makes it 1 to the negative 2, which is just 1. If I have 1, oops, I shouldn't write 1 there. If I have just 1, notice 1 plus 1, that's again 1, that's again 2 to the negative 2, that's 1/4. And notice the positive and negative values, the sign gets scrubbed there, so this is 5 to the negative 2, again 1/25. So if you're thinking about what shape is that, well, here's what you should sort of be thinking about. The largest output value we have is 1 here, and the values that I used for my inputs are negative 2, negative 1, 0, 1, 2. So we have negative 2, 1/25, that's really small, negative 1, 1/4, 1, 0, 1, and then it's a symmetric shape here. So you're looking at something that looks like that, I guess. Okay? And then what about this one? Well, notice this is 2 minus exactly the same thing over here. So what do we have? Well, if you were going to do a set of values again, you'd put in negative 2. It's 2 minus a 25th. Negative 1 is, what is that? 2 minus 1/4. 0, that's going to be 2 minus 1, or 1. At 1, it's 2 minus a 4th. At 2, it's 2 minus a 25th. So a lot of these values, this is really, really close to 2 up here. Then it comes down, it actually comes down to that value, and then it comes back up. So we have sort of a symmetric shape here, then x equals 2. Okay, so this is the region that we're looking at. And remember, the problem said we're rotating around the y-axis. So here's the region. We're rotating around the y-axis. It said to use the method of cylindrical shells. So we're cutting parallel to the axis of rotation. Maybe I've got a box right here, and I'm going to be rotating that around. And so you remember for cylindrical shells what I've got is I've got essentially the volume equals 2 pi r, that's the circumference, 2 pi r times the height. I've got to figure out what those are. Now, which direction am I cutting here? I'm cutting along the x-axis, so dx from, and I'm going to start cutting. These slices are going to start at 0 and end at 2, 0 to 2. Well, what's the radius for a particular slice? So if I had a particular slice out here, how far is it? Well, that slice has to be allowed to vary. So that radius here is actually x. So what I'm really going to have here is 2 pi integral from 0 to 2 of x times, then what's the height of this box? Well, it's the top minus the bottom, right? And the top is this function. The bottom is this function. So let's see. I've got that 2 minus x squared plus 1 to the negative 2 minus the bottom. Well, if I've got minus this and minus another one, permit me to write 2 minus 2 x squared plus 1 to the negative 2 dx. Now, if you're looking at this and you're saying, ooh, I'm not sure I really want to integrate that, I might agree. So sort of one of our key techniques is to say, well, if you could just sort of cover up some piece, would it look nicer? And the answer is certainly yes. If I could cover that piece up right there, it would look way nicer. This function inside a function is really a mess. So that cries out for u substitution. What if u were x squared plus 1? If I could get rid of that piece, wouldn't life be better? Well, if I did, du would be 2x dx. Now this turns out really well because I have a dx, I have an x, and I actually have a 2. So putting those three things together, they're all already multiplied, is just du. Now some people change their limits of integration, some people don't. Let's go ahead and change ours. This is integrating from x equals 0. Well, if x equals 0, notice that means u equals 1 up here. So the integral from u equals 1. If x equals 2, notice u equals 5 up here. So integral from 1 to 5 of now the 2, the x, and the dx all just become du. 2 stays 2 minus 2, this is u to the negative 2. Okay, and that I'm able to integrate. So pi times the integral of 2 in terms of u is just 2u minus 2 integral of u to the negative 2 is u to the negative 1 divided by negative 1. Well, that just changes the sign from 1 to 5. Okay, so plugging in 5, we get 10 plus, let's see, 2/5, and then minus pi times plugging in 1, 2 plus 2. So everything is times pi. I'll just put the pi there. I've got 10 minus 4, that's 6 and 2/5 pi. That might be a little confusing. Somebody might think I was multiplying, so I'll just write that as 32/5 pi. That is the volume of this surface.